force that would be exerted on a dipole in the presence of an electric field. And we found that the fundamental effect of an electric field was to produce a torque rather than a force, but that we could find the force. So our dipole consisted of two charges separated by a distance L, and you had an electric field E. If this is the position R relative to our origin, then the electric field at this point was R plus E evaluated at R plus L over 2, and the electric field at this point was E evaluated at R minus L over 2. Now, we could then find the torque. The torque will be due to the force on this one crossed this distance crossed into that force. Remember that torque was R cross F from last semester. And so it would be at this location, the R is L over 2, crossed into the force, which was QE, evaluated at R plus L over 2. And down here, the difference is that L, the R points in the opposite direction. So it was minus L over 2, but the charge is also minus E at R minus L over 2. And so those two will add, and you will get QL crossed into. Now, the difference between these two is infinitesimal, because it's just grad E dot L over 2. And so to first order, this will just be E of R. Then there is an additional term which would be the gradients, but in the limit in which L becomes small and this becomes a dipole, you will simply get this. So this will be P cross E. Understand what we did there? Let me write it out for you in one more step. This should be, each of these becomes QL over 2 crossed into, first this one, E of R plus L over 2, and then minus E, plus, because the two signs there, minus L over 2. But we know what this is. This is P over 2. For this one, we write E of R plus grad E dot L over 2 plus E of R minus grad E dot L over 2. So these terms cancel out. And we simply get 2E of R over 2, which gives you P cross E. So that the torque exerted on a dipole in a field is just the dipole crossed into the field. Okay with everybody? But when we wanted to find the force, then it was QE evaluated at R plus L over 2 minus QE evaluated at R minus L over 2. And this time, it's the E's that cancel out instead of the gradient terms. So you had Q times E of R plus grad E dotted into L over 2 minus E of r minus grad E dot L over 2. And this time, the E of r's cancel out, but these terms add. So what we got was QL, Q times grad E dot L, which was then grad E dotted into P. So that was the force we expected to get. That was okay with everybody? Yes.
Why are you using grad and then the dot product on like the grad E dot L2? Okay.
Because what I need is, I need this thing. Okay? So I write out what this is. It's E of r plus grad E dot L over 2. And why is that? Because E of r plus L over 2. That would consist of, in the x direction, it would be Ex of r plus L over 2, plus the y stuff, and so on. Now, what is this? It's Ex evaluated at r plus the change in Ex as you go from r to r plus L over 2. And that will be the change in Ex with respect to x times the distance you go in x, plus the change with respect to y times the distance you go in y. So it would be the Ex dx times Lx over 2, because that's how much you would change when you moved Lx in the x direction. But then you would also move in the y direction, and you would also move in the z direction. So you got Ex of r. Now what is this? That is d by dx of Ex Lx plus d by dy Ex Ly, d by dz Ex Lz. So that is, you got 1/2 from this, and then you've got the gradient of Ex. That's dx dx, dx dy, dx dz, dotted into L. So that's the x direction. If we did the y direction, this would just become a y. If we did the z direction, it would just become a z. So the whole thing then is E plus this. In other words, writing it out, this will be equal to E of r plus, in the x direction, the gradient of Ex dotted into L. In the y direction, the gradient of Ey dotted into L. And in the z direction, the gradient of Ez dotted into L. Okay? Now, to see that that's the same as this, all you have to do is evaluate that thing. And so for grad E, what you had was x hat d by dx plus y hat d by dy plus d hat d by dz multiplied with no dots and no crosses. And so what did this become? You had an x hat here. D by dx didn't do anything to that. So you had dx dx x hat plus x hat dey dx y hat plus x hat dez dx z hat. So that was this term. And then you did this one. Y hat dex dy x hat plus y hat dey dy y hat plus y hat dez dy z hat. That was just applying that. And then finally, you had x hat de hat plus y hat dez dy y hat plus z hat dez dz z hat. Just writing out each of those terms. That was okay with everybody? Okay. Now we dotted this thing into L. So grad E dotted into L. Now that is grad E dotted into Lx x hat plus Ly y hat plus Lz z hat. So now you take this dotted into the right-hand side of everything here. And so what you got, x hat dot x hat, that's 1. So you got x hat dex dx lx. X hat dot y hat 0, 0, 1. So you got y hat dex dy lx. Y hat dex dy lx. And then that's 0, that's 0. This one will give you x hat dez dx lx. And this is 0, and this is 0. Everybody understand what we're doing? We're just not. That's right, exactly. When I dot this into here, I get x hat dotted to whatever's on the right-hand side. And so I've got this term, that's 1. So that gives you this one. Nothing there, nothing there. And now I've got this one. And that will give you y hat dex dy, y hat dex dy times lx. Nothing here, nothing here. And then this one, dez dx lx with the x in front. And now I do the Ly terms. That'll be 0, that'll be 1. So I'll get x hat dEy dx Ly. 0, 0, this will be 1. Plus y hat dEy dy Ly. That'll be 0, that'll be 0, that'll be 1. Plus y hat dEz dy Ly. Yes?
On your graph, you should the last three there start with z hat. Like the first.
Whereabouts here?
So your second line of the, so down a little bit more. Yeah, that one, shouldn't it all start with z hat?
What I'm doing is I'm calculating this one. Yeah, I mixed these up, didn't I? So it's x hat. I'm doing this one first. Dex dx, dey dx, dez dx. Now I'm doing the y ones. Dex dy, dey dy, dez dy. And then I'm doing this one. So this should be z's. Yes, thank you. And so that is thank you. Dex dz, z hat, dey dz, and z hat, dez dz. Yes, those two are wrong. Thank you. Okay, so when I went through here and I dotted into the x, I picked up this one, I picked up this one, I picked up the last one, which should be dex dz, dx dz times Lx. Now when I did the y's, I picked up this one, dey dx Ly, dey dy Ly, and then this one, z hat dez dz, z hat dey dz. Okay, and then I had the z hat terms, this guy. So I picked up this one, plus x hat dez dx Lx. This one, y hat dez dy Lz, and this one, plus which one? Third term in? Yeah, that should be z hat. Thank you. Okay. Now, collect the x terms together. And what do you get? Let's do that over here. So if we collect these terms, we got this one, dex dx Lx. got this one, DEY LX LY. DY DX LY. And we've got DEZ DX This was LZ, was it not? Let's see. This is dotting LZ into this, and that gave you I dotted these, I got these three. So this one came about from dotting this into this. So I got DEX, DZ, LZ. Okay. Okay. DZ, DX, LZ. So that was X hat. And then we had Y hat. We had X. And we had DEY, DY, LY. And we had DEZ, DY, LZ. And then finally for Z, we had DEX, DZ, LX. And DEY, DZ, LY. And DEZ, DZ, LZ. So that's what you got for the force. But if you look at this, this is d by dx of EXLX, EYLY, EZLZ. So that is x hat d by dx of L dot E, or E dot L, doesn't matter. And this one is the same thing, only derivatives with respect to y. Y hat d by dy E dot L, and z hat d by dz of E dot L. But that is just the gradient of E dot L. And so when you put in the Q that we had, what we got was the force was equal to the gradient of P dot E. And that's the result we got on Friday. That the force, you have to find the gradient of P dot E, but that's obvious. And the reason it's obvious is the force should ultimately be minus the gradient of the potential energy. Right? That's what we got when we talked about potential energy last semester. That means that this says the potential energy is minus P dot E. Well, of course it is, because when the things line up, the dipole lines up with the field, the energy is its lowest value. And when it's perpendicular to the field, the energy is opposite to the field, the energy is the highest value. Or you can look at it another way. This is equal to minus the gradient of the potential energy. But suppose you had a dipole in an electric field. Here's the electric field. Now, let's choose lined up as the lowest potential energy when it's lined up. Then, to move this thing, you have a torque, which we've already discovered was P cross E, which in other words was PE sine theta. And now you move it a distance d theta, and the work you do, dW, is the torque times the angle, and therefore it's the integral of this, which gives you minus PE cosine theta. But PE cosine theta is simply P dot E. And so you get exactly what you would have expected to get. That the force is the gradient of minus the gradient of the potential energy, and the potential energy is minus P dot E. Okay with everybody? So we went through a lot of grisly arithmetic. I could have just started with the potential energy. I did this just to give you practice with vectors. Me practice with vectors too, since it took me 4 attempts to get all the figures right. The physics of it makes sense? Okay. So now, armed with that, what we want to do is to find the force between two dipoles. You got a dipole P1, and you got another dipole P2, located a distance r from the first. And we want to find the force between those two dipoles. So this is Coulomb's law for dipoles. We previously did the force between 2-point charges. Now we're going to do the force between two dipoles. So how do we do it? Well, we need the gradient of P dot E. But we know what E is. E is the electric field due to a dipole, which we've already worked out. So let's just write it down. We need the force is equal to the gradient of P2, because that's the one we're finding the force on, times the electric field due to P1. But the electric field due to P1 is K over R cubed times 3 P1 dot R hat times R hat minus P1. That was the equation, the form we got for the electric field produced by a dipole. So this will be the gradient of P2 dotted into this. That will be K over R cubed. This will be P2 dot R hat. So 3 P2 dot R hat times P1 dot R hat. That's this term. And then we have minus K over R cubed P1 dot P2. So now what we got to do is take the gradient of that. Okay. So now we just use our usual vector rules. So this is equal to K. That's a constant. So that'll factor outside. I'm going to replace R hat by R over vector R over the magnitude of R, which will make this 3. Then I will have the gradient of P2 dot R times P1 dot R over R to the 5th. Because each one of these is vector R divided by magnitude R. There are 2 of them. That'll make R to the 5th. Minus the gradient of P1 dot P2 over R cubed. Okay, so now we know that the gradient of the product of 2 scalars is the gradient of the first times the second plus the first times the gradient of the second. So this would be the gradient of this guy, gradient of P2 dot R times P1 dot R, and then that thing times the second, R to the 5th, plus the first one, P1 dot R times P2 dot R times the gradient of the second, 1 over R to the 5th. Now we do the same thing here. Minus the gradient of P1 dot P2 divided by R cubed minus the gradient minus P1 dot P2 times the gradient of 1 over R cubed. All we've done is to use the fact that the gradient of AB is grad A times B plus A times the gradient of B. It's just the product rule. Okay, so far? All right. So now, okay. Now, the gradient of a product is, use that rule again. So we get 3 over r to the 5th times, that'd be the gradient of P2 dot r times plus P2 dot r times the gradient of P1 dot r. Now we got this one. That'll be plus P1 dot r times P2 dot r times the gradient of 1 over r to the 5th. But that is just minus 5, 1 over r to the 6th, r hat. And why is that? Because in spherical coordinates, you have r hat d by dr plus theta hat over r d by d theta plus phi hat over r sine theta d by d phi applied to r hat. Okay? This one gives you the derivative of this, which is 1 times, well, not r hat, it's 1 over r to the 5th. Right here. And so when you do this, this one gives you minus 5 r hat 1 over r to the 6th, and all the others give you 0 because r is not theta and it's not phi. So you just get minus 5 over r to the 6th times r hat. And then you got this one. Now, those are constants. That's just the dipoles. So that term is 0. This one will give you minus 3 r hat over r to the 4th. The two minus signs make it a plus. 3 P1 dot P2 r hat over r to the 4th. Here there was still a factor of 3 because of that 3. And so here I had 3 made this a 15 instead of a 3. Okay with everybody? Yes.
So how is grad P2 dot r, all that stuff, how is that different than what directly is right?
This is the product of these two times the gradient of that. This is the gradient of those two times this. We're just doing this relation over here, where the A is those two dot products. The B is 1 over r to the 5th. And so first I have this guy. I'm now writing it out as using that again. It's the gradient of this one times that plus this times the gradient of that. Okay. Almost done. We need to figure out what this is. The gradient of the dot product of two vectors. We got to figure that out. All right, now to do that, we're going to use the vector cross product. A cross B cross C is C dot A times B minus B dot A times C. Okay? Now, since we want to end up with divergence of A cross B, we better let's make C grad, and we can take that to be B, and that to be A. Okay? So, we know that we have to apply this to both A and B, because that's the rule for derivatives. You have to apply it to both of them. So first, let's apply it to B. Well, our second rule is that we are to put the derivative on the left of what it's operating on. So we're going to write this term as A cross, now, to get this on the right, we have to put in a minus sign, because the cross product, you reverse. When you change the order, you get a minus sign. So that gives you a minus del cross B. Okay? Now, the dot product doesn't matter what the order is, but we want this just to the left of this. We want the C to operate on B, so this will be A dot del on B. And here we want this operating on that stuff. It's just multiplying it, so I can just move it to the other side. And I get minus gradient A dot B. So let's put this over here, that over there, and we get gradient A dot B equals A dot del on B. Now this comes over here, it becomes a plus A cross the curl of B. So that's operating on B. Now I have to operate on A. Well, the dot product is the same A dot B as B dot A, so there won't be any sign change in reversing these. So I'll get the same terms except interchanging A and B. So I'll get B dot del on A plus B cross the curl of A. So that is the gradient of the dot product of two vectors. Okay. Now, we're interested in the gradient of, say, P2 dot R. So that means the gradient of P2 dot R, take A to be P2, B to be R. The derivatives of P2 are 0, so these terms are gone, because P2 is a constant. So all we have is this. So it'll be P2 dot del operating on R plus P2 crossed into the curl of R. Okay? So now we got to evaluate those two things. But those are easy. P2 dot del on R. What is that? That is Px d by dx plus Py d by dy plus Pz d by dz operating on x hat, y hat, z hat. So now do it. D by dx makes that a 1, and you get x hat. The other two are 0 because this doesn't depend on x, and that doesn't depend on x. So you get px x hat. Do it on this one, you get py y hat. Do it on this one, you get pz z hat, but that's just p. So P2 dot del operating on R is just P2. So this piece is easy. Now, what is the curl of R? Well, that's easy. So the curl of R, that's R hat d by dr plus theta hat over R d by d theta plus phi hat over R sine theta d by d phi crossed into R hat. Okay, so first this one, R hat crossed. Now, the derivative of R with respect to R is 1. So you get R hat. The derivative of R hat with respect to R is 0. Theta hat over R crossed, the derivative with respect to theta, well, that's 0. And so you get R. The derivative of R hat with respect to theta, you remember, was theta hat. And then you've got phi hat over R sine theta, and derivative of that is 0. Derivative of R hat with respect to phi hat is some constant in the phi direction. That's 0, that's 0, that's 0. So the curl of R is equal to 0. So now we have everything we need to finish the problem. Still alive after this nightmare? So now we can write down the answer. We know that this thing was just P2. So we get P2 times P1 dot R hat. So we get P2 times P1 dot R. And here this is P1 times P2 dot R. This is minus 15 over r to the 6 times that. Minus 15 over r to the 6, r hat times P1 dot r, P2 dot r. P1 dot r, P2 dot r. And lastly, 3 P1 dot P2 P1 dot P2 r hat over r to the 4th. Now r is r hat times r, and similarly here. So we can replace those by r hats and this by an r to the 4th. So we'll get k over r to the 4th times 3 P2 times P1 dot r hat plus 3 times P1 P2 dot r hat minus 15 P1 dot r hat P2 dot r hat r hat plus 3 P1 dot P2 times r hat. And that is the force between two dipoles. Now let's look at a special case. And that special case is one dipole here, another dipole parallel to it along the line that it points in. So this distance is r, and this is P1, this is P2. P1 dot r, since P1 points in the direction of r, that's just P1, that's just P2, and so we get k over r to the 4th times 3. Both of the p's are in the same direction, and let's call that direction the z direction. So we got a z hat, and we've got 3 P1 P2, 3 P1 P2, so that gives us 6 P1 P2 minus 15. These each point in the same direction as r, so that's P1 P2, and they're all pointing all these things are z. And here, 3 P1 P2. Nine minus 15 is minus 6. So you get minus 6 k P1 P2 over r to the 4th in the z direction. So you get an attraction between the two, which is minus 6 k P1 P2 over r to the 4th. Now, why is that? Because as charge is separated by distances, what you have is minus q, q, l, minus q, q, l, and the force is the sum of 4 terms. It'll be this one on this one, that'll be a negative sign, it'll be attractive, and it'll be k q squared, and the distance between them is L is the R, and you moved L over 2 each way, so it's R minus L quantity squared. And then you'll have this one on this one. That'll be repulsive. Okay, q squared. And those will just be L, because they're each shifted the same amount. And then you'll have this one on this one. That will also be repulsive, shifted by the same amount. And finally, you will have this one on this one. That will be attractive, and it will be K q squared. And this time it'll be R plus L squared. Okay, so that is minus, it is kq squared times minus. Now, factor an R out of this thing. And so I'm going to put an R squared down here. And I'll have minus 1 over 1 minus L over R squared plus 2. I factored the L out, so that's just, this is R squared, sorry. I factored the R squared out, so that's just plus. Here I will have 1 over 1 plus L over R squared. Now just expand by the usual Taylor's theorem, and you got K q squared over R squared times, that'll be 1 plus 2 L over R, plus 2, minus 1 plus 2 L over R. Okay, I've got, let's see, is this right? Yeah, that one. And so this was a minus. And so what you've got is those cancel out. You get 4, I missed something here. Okay, I missed a number here someplace. Anyway, we'll work that out next time, but you'll get the same answer.